Alright, today we're going to look at logarithmic expressions and equations. So yesterday we were doing graphing. Today we're going to look at more of the equations and solving them mathematically. Basically the key idea is a log expression and the graphs. They're pretty similar to exponent graphs and equations. So often we're going to be able to convert them from one to the other to be able to solve, whichever way is going to work better for us. The way you can kind of connect them is you often can think that a log is like an exponent. So in other words, if I had the equation log b of x, it would ask what exponent would be on the base b that would give x as the value. So in other words, we're basically saying b to the power of what would equal x. Is kind of how we connect the logs and exponents together. Yesterday when we looked at graphing, so I just resketched the graphs here, so our blue graph is y equals 10 to the x, and I said yesterday the log graph is basically the same graph with a diagonal reflection. So you can see the y-intercept on the original graph of 1 now becomes the x-intercept on the new graph, and before your domain was any real number for x, it's now any real number for y, and the range was greater than 0 for the y, it now becomes greater than 0 for x. So what's happening is we're actually just sort of flip-flopping the x and y coordinates. So y equals log x is actually the exact same thing as x equals 10 to the y. So if you kind of compare the two graphs, so the original graph, y equals 10 to the x, the blue one, and the new graph, the red one, x equals 10 to the y, you can see that they're basically the same equation, just sort of the x and y have traded spots. So because of that, we can always convert from one equation to the other. So yesterday, somebody in class asked, well, how come if these two graphs are the same, why is y equals 10 to the x similar to log x? Like, where's the 10? So in the original equation, we had 10 to the power of x. Here we got log of just x. The question was, where did the 10 go? So what happens is with logarithms, we just basically looked at basic logarithms yesterday, but in reality a logarithm has a base number, so it'll be log of some sort of base to some sort of other number. So the equation that we did yesterday, y equals log x, is actually in reality equal to y equals log base 10 of x. But we don't normally need to write the 10. So just like when you do, if I said the square root of a number, like square root of 4, in reality when we write square roots there should be a little 2 out front, but we can skip the 2 because it's the most common one. Just like if I said, if I have x by an exponent by itself, that's the same thing as having it x to the power of 1, those kind of ideas. So when we write just y equals log x, in reality we're talking about y equals log base 10 of x. So the base 10 is sort of the standard one, and we don't need to always put the 10 in. So you can see now, where is that 10 coming from? In the original exponential equation, it actually shows up as the base number in the logarithm equation. Your calculator button, so when you hit on your calculator, you hit the log button, it's on the left hand side. When you hit log, it automatically assumes you're doing base 10. It's sort of the standard. So on our formula sheet that you get when you write the diploma, they actually give you the conversion to switch from a regular exponential equation over to a log equation. So you can have your equation as y equals a to the x, or that same equation would then switch to x equals log a to the y. So they're a little bit weird to convert back and forth, but once you do a few of them, you'll get the idea. And the neat thing is you can switch it whichever way you want to make it easier to solve. So let's do a few examples to kind of show you what I mean. So if we were trying to solve a log equation, so let's say I give you log base 2 of 16, and the question is, what is that equal to? Because we already know how to solve some basic exponential equations, maybe it's going to be easier to solve it as an exponent. So if we switch it, if we use what's above and we switch it back to an exponential equation, then that means that really what we're solving is the y in this case is our 16. So we'd have 16 would equal our a is our base number, which is 2, and n, the answer that we're looking for, is now our exponent. So log 2 of 16 equals n, we can change that to 16 equals 2 to the n, and then now that we have it switched to an exponential equation, we can use the same strategies we used in the last unit. we can change the bases to be the same, and then if the bases are the same, the exponents have to be the same, or you could solve it by graphing. So let's do the math way first. So 16 can be changed to 2 to the power of 4, right? 2 times 2 is 4, times 2 again would be 8, times 2 again would be 16. So 16 is 2 to the 4, so we can change 16 to 2 to the 4. That means our n, I made a mistake there, so our 2 to the 4 then will equal 2 to the n, so that means n has to equal 4, and we're done the question. Okay, or like I said, you could also solve this by graphing. In the last unit, when we had these easy ones that we could solve by changing the base, it worked well. Or the other option, remember, is just graph y equals 16, graph y equals 2 to the n, plot your graph, so you'd end up getting basically the y equals 16 would be a straight line, y equals 2 to the n would be a curve, something like that. Find your intersection point, and that intersection point will happen at x equals 4. So we will get the exact same answer whether you solve by mathematically or graphing. Okay. The good news is with graphing it'll always work. The bad news is it takes you time to plug in the numbers and find the intersection point and so on. What we're going to look at today is how can we solve these actually using logs instead of exponents or graphing, and most of you I think are going to find that it's a better, easier way to go. Okay, so let's look at another example. So if I give you the log of base 3 to a fraction, so the good thing is with these you can solve them with their fractions, decimals, it doesn't really make any difference. Use the same formula, so we want to change this now. So the base 3 to the power of x is going to equal 1 over 27. Okay, so once again you could solve it by graphing or making the bases the same, whichever you want. To make it faster, let's make them the bases the same again. Okay, so I'm going to make it 3 to the x equals 1 over 27 is the same thing as 1 over 3 to the power of 3. 3 times 3 is 9, times 3 again is 27. And remember the rule that if it's a fraction, you can write that as 3 to the negative 3. So from that we know that x has to equal negative 3. And we're done. Okay, so now what we're going to do is what happens if we get one where the bases don't work. So let's try one like log 3 to the base 5 equals n. So the question is, what does our n have to equal? So this is one where if we use the formula and convert it, we would get 3 to the n equals 5. So that's good, that's easy enough to switch. But now the problem is, how do we solve it? Okay, we can't solve by changing bases because we can't get the 3 and 5 to be the same base. Okay, we could still graph. Graphing would work, but it would take a little bit of time. Okay, so the other option is, what else can we do? And there is sort of a neat formula that's on your formula sheet. And the idea is we can actually solve these things by actually using the logs. So instead of changing it to an exponent and trying to figure it out that way or by graphing, we can actually use these by using a new log formula. And it's on your formula sheet. And the one we want to use on the formula sheet, they write it as log b to the c equals log a to the c divided by log b to the c. Okay, looks confusing when you look at it like this. Oh, sorry, I made a mistake. It's log a to the c divided by log a to the b. So like I said, it looks confusing, like we got b and c, which are just some numbers. A is going to be some other numbers. So, and you can make that number whatever you want. So for example, if I gave you log, the question that I just had on the previous page was log 3 to the 5, what we can do is we can actually solve that by going log 5 to the whatever base we want, but let's make it base 10 because that's the one our calculator can do. We can make that log base 10 divided by log 10 base 5 divided by log 10 of 3. So now when you can actually do this on your calculator, you just got to type it in as log 5 divided by log 3. Do that on your calculator, it gives you an answer of 1.46, which is the correct answer. Okay, so the nice part with logarithms is even if they're not base 10, we can still solve them. You just have to basically do log of the big number divided by log of the small number. And do that on your calculator and it works every time. So let's do a couple more examples. So if I gave you log 2 of 7, so what you want to do is, instead of changing it to an exponent, remember we could write that as 2 to the power of what equals 7. Right, that's the way we could convert it to an exponent, but then we still can't change the basis, so that doesn't help us much. So our better solution is from just leave it in log form and solve it as log 7 divided by log 2. So we do that on our calculator, log 7, just type it in exactly like that, log 7 divided by log 2. We get an answer of 2.81 if we round off the decimal. Okay, so quite often what we want to do is we want to use the logs to solve rather than the exponents because they're going to be usually quite a bit easier and simpler to figure out on your calculator. So we'll do a couple more examples and that'll be it for today. So let's try one now where if I give it to you in exponent form, if I gave you 81 equals 10 to the x. So the question is, how do we solve that? So we can't make the bases the same. That's no good. So now what we want to do is we want to switch it back into a log form. So if we use that old formula, and it's good to have the formula sheet handy because you can always switch back to it, but we want to change 81 equals 10 to the x, change it to a log, so you'd have log of base 10. So remember that 10 moves down to your base number. The 81 goes over to the main number, so you can kind of see what I'm doing here. So the 10 goes down, the 81 goes over, and that's going to equal x. So we have log 10 of 81. Well, we know how to do that. We can just basically use the new formula. That'll equal log 81 divided by log 10. Plug that in on your calculator, and you're done. So you can type it in like this, log 81 over log 10, which will give us 1.908. But we actually did more work than we need to because we already know from before our calculator is automatically programmed to do log base 10. So in this case we actually don't have to do the division. We can just type in log 81 directly and that would give us the exact same answer as well. Okay, so when you're doing these exponential equations, they're pretty tough to solve. Change into logs, they're pretty easy. So in this case, just change the 10, make it log of 81, type it in on your calculator, you're done. But if you even forgot that, you could always go back to this division idea and you would get the exact same answer either way. So let's do one or two more and then we'll stop. So if I gave you the equation 10 equals 4 to the x, let's try to solve that one. So we can't, so what we do is we change it to log 4 base of 10 will equal x, right? Change it to the logarithm equation. Now from there we can go log 10 divided by log 4. Type that in on your calculator. It'll give you 1.66 and you're finished. If you're not sure you did it right, just remember you can always go back to the original equation. So our original equation was 10 equals 4 to the x. And on your calculator, you can actually just see if it's true. If you actually put the 1.66 answer that we just got, so if you go 4 to the 1.66 on your calculator, you will see that it is equal 10. So we know that we did it right. So that's it for today. We're just using logs and exponents to convert back and forth to solve. Hopefully you guys are going to see that the logs are an easier, faster way to solve these things rather than trying to solve exponential equations. And graphing is same thing. It's going to take you too long, so you're better off to just switch into logs. The hard part is using that formula to remember how to switch. So you remember you always want to be able to go from an exponent. You want to be able to change that into a logarithm. So that same equation would become x equals log a of y. So as long as you can make that trade back and forth, you can change them to exponential equations, and then remember, even if you got logs that weren't base 10, so if I gave you log 8 of 12, okay, you can't just type it in on your calculator, you have to go log 12 divided by log 8. Do that on your calculator, it'll work, and you'll have your answer. Okay? If they happen to do be base 10, remember that if it's log base 10 of anything, it doesn't matter what the number is, you don't need to put in the base 10, you don't need to do the dividing, you can just type in log 50 and that would give you the correct answer as well. Okay, so we'll stop there. I'll post, are you ready to do the worksheet? The worksheet is 7.2, there's a bunch of practice questions on this stuff. Have that done and we'll do our next lesson tomorrow.